Hello, my name is Mylee, and this is our capstone project for MAD2502, our project. So we decided to use data from Spotify and the Billboard Hot 100 to predict what songs will be most popular. We acquired our data from Kaggle, and the inspiration came from the GitHub Spotify Music Analysis Popularity Prediction. Throughout this presentation, we will refer to several numerical features from Billboard and Spotify, respectively. So from Billboard, we have things like peak rank, where it's how high a certain song has gotten to on the Billboard Hot 100, weeks on board, how long it's been there, and more. For Spotify, we have many more numerical features, but here are some prominent ones. Duration, or how long a song lasts, how loud a song is, speechiness, how wordy it is, danceability, how danceable it is, and more. Importing packages. So for this presentation, we had to import many packages, but here are some of the most prominent ones. We have NumPy, which is used for numerical computing, Pandas, which manipulates and analyzes data by providing data structures, Matplotlib, which is capable of creating many types of plots for visualizing data, and DateTime, which can manipulate how a date is presented. Reading the files. So again, we got our data from Kaggle, and we acquired Spotify data and data from the Billboard charts. So we used Pandas to open and read the files. The Billboard charts data had about 330,000 songs on it, since it consisted of 100 songs from each week from the years 1958 to 2021. And the Spotify data had about 170,000 rows or songs on the file, on the CSV file. So it doesn't include every single song from about sometime in the 1900s to present day, but it included some of the most prominent ones from Spotify. So my responsibility for this project was to be in charge of the data cleaning. So we first used the date time package to transform the date to only the year. Since both of the CSV files containing Billboard and Spotify data included dates where it had the month, date, and year, we only wanted the year by itself. And the second code below here organizes the Spotify data to only include songs from the year 2000 and above. We tried to only have it in the 2020, so 2020 and 2021, but we didn't get enough data out of that. And for the Billboard data, we included the years 2020 to 2021 only, because each year there's 52 weeks in a year and 100 songs per week. So we had more than enough data for the Billboard price. So for the Billboard cleaning, the code over here on the left goes through and looks and sees if there are any duplicates for each song. And the code on the right is a for loop, which will iterate songs over and over for each group. And it will only keep the songs that have the highest peak rank and delete all the other duplicates. So for the Spotify cleaning, we took inspiration from the people that had the GitHub. And first, we concatenated the artists and names by joining them together. And the code down below checks the duplicates between the two groups, the Billboard and the Spotify. So what I did was I checked to see and keep the Spotify data that had the same songs from the Billboard data. For the exploratory data analysis, we noticed that in Spotify, it had the duration of the song, but it was in milliseconds. People don't normally measure songs in milliseconds, so we had to divide it by 60,000 in order to turn it into minutes. And the table down below describes the analysis of each of the important columns, so like acousticness, danceability, stuff like that. So it includes like the count, like how many, the mean or the average, stuff like that.
I'm Taylor. I did most of the data visualization and the trend visualization. So I first started out with the Spotify data set, and I did a bunch of attribute graphs for the Spotify data. I based it heavily on the GitHub code, but also we used our own data, and I took out some of the attributes that we didn't think was necessary. So we used Matplotlib and the Seaborn imports to visualize each of the attributes with the Spotify data-5. And what I thought was most important, we did song key, acousticness, danceability, liveliness, tempo, duration, loudness, and energy. So I think those were definitely the most important to look at in terms of trend wise. So on the right is the code for the graph below it. And this was just an example of one of the attribute graphs that I did for the song key. And we did this on the Spotify data set. And then this is another slide with some of the attribute data graphs. So this one is for the song loudness, and then the smaller one on the bottom left is for the explicit, which was coded as 1, or non-explicit coded as 0 for the Spotify data. And then on the right, I just did an aggregate for all of the graphs, just so you could look at all of the attributes at once. And we took out some of the ones that we didn't think were very important. So we took out valence. We didn't look at that at all. And then we did some visualization with the Billboard data that we used to compare kind of the trends in each of the data sets. So I also did some attribute graphs for this data set and used the same imports, Matplotlib and Seaborn. But for the Billboard data, we didn't have like song characteristic data. We just had peak rank and rank values. So to help with analysis later on, we visualized those variables with the Billboard data set. So on the right again is the code above for the graph for the song ranks. And then this is a graph for the peak ranks for the Billboard data. We did some more visualization for the Billboard data. We did tables as well, so you can see side by side different statistics on the rank and peak rank of the data set for the Billboard data. Just like used further, we did it to compare the Spotify data and Billboard data more easily to verify the accuracy of the model. And then I did a graph visualizing the Spotify data attributes. This was especially helpful, just seeing everything put together. So on the left is the code for it. We took out some of the attributes again, and this graph is more of the ones that we thought were important. So we have acousticness, danceability, energy, instrumentalness, liveliness, and speechiness for the characteristics of the song. And this was for the Spotify data. And then I added an extra one for tempo because it wasn't sitting nicely in the original attribute graph. In the original attribute graph here. But I thought this was interesting just to see how the tempo of songs has increased over time, over the years. And then this is a aggregate graph set for the ranges of Spotify data. This was included in the original GitHub code, and I did not change this. So just wanted to point that out, but I also wanted to bring it up just because I think it is an interesting graph to look at. And this is showing the ranges of each of the variables. So like acousticness, danceability, duration, energy, etc. So you can kind of see like what scale you're working with. So you're not just looking at like an energy score and being like, okay, what does that mean? So this is helpful in terms of like thinking about your data relatively and what it means. It's not just a number score. So this is just the last slide. I thought it would be interesting to do a box plot for some of the data that didn't have binary inputs. So you could kind of see outliers and where the general like middle of the data is. So I did that with danceability and tempo, and then above is the code that I used.
Hi, I'm Adrianna. I did the statistical analysis part of the project. Before we got into any formal stats and statistical analysis tests, we did some informal stats and inferences based on just what the data was showing us. So we started out with this heat map based on the open source code, and we saw that there was a lot of noise going on in the data. There's a lot of variation in color, which is a variation in correlation between each attribute, and we assumed the same would hold true for the Billboard data. So in an effort to mitigate this amount of noise, we created this new data frame, artist mean, which takes the peak rank mean for each artist and attributes it to them. From there, we merged that data frame to the original Billboard chart data frame and created a heat map. So there's a lot less noise in this heat map, but there is still some noise, specifically with peak rank mean, peak rank artist, and then rank itself. So peak rank and rank seem to have a lot going on and needed to be investigated. From there, we did some hypothesis testing. We created visualizations of the distributions between peak rank and rank. From the open source code, there was danceability cut by explicit, which is just if the song's explicit or not, does it affect its danceability? For Billboard chart data, it was the overall rank, like the peak rank, the highest it reached, compared to the overall rank by week, which varied a lot. For both distributions, after conducting an ANOVA test analysis of variation, we found that both distributions were different. We rejected them all. But what was interesting for the Billboard chart data for rank and peak rank was this initial peak for peak rank and then a drop off later. And this peak and drop off indicated to us maybe there's something going on with time as a variable for this data. So we conducted another hypothesis test, this time with the mean peak rank of songs by month. And we did a little histogram for that. And we saw that November had this peak, but then there's a drop off in December, and then it goes right back up in January. So we thought that was a little bit odd. We wanted to investigate that a little bit more. We printed out the top 3 songs for each month. We paid special attention to November, December, and January, just because they were a bit odd in the distribution. And while November and January had songs varying a bit more from the season, I guess, and varying in genre, for December, All I Want for Christmas Is You suddenly shoots up as a peak song. So we decided to just print the songs from January, November, and December. And even though you can't see it here, if you were to scroll down through the entire output, which is a lot, half the songs become just Christmas songs. So from there, we decided to filter for the songs in the data frame that had Christmas related words. So Christmas, snow, Rudolph, Jingle Bells, anything like that. And this isn't the full list, but there were a lot of songs from month 12 and 11 and 1 that had Christmas related words in them. From there, we printed out this visualization of the distributions between Christmas songs and non-Christmas songs. For Christmas songs, we see that drop off that was visualized before. So it's like this peak and then drops off, while non-Christmas songs remain a little bit more stable throughout the year because they're not made for a specific season. The same was done with explicit and balance. Balance is just how upbeat a song is, like the general vibe of the song. We wanted to see if explicit would affect that. So based on the open source code, we did that. And this is also visibly different, but again, you can't know until you conduct a test. And we did with ANOVA, analysis variance, both distributions were different. Now, just knowing that the distributions are different, it indicates that there's something going on there, but not necessarily the relationship between the variables. So we decided to just keep an eye on these variables, but we still wanted to know what was going on between artist and peak rank. So we conducted a chi-square test for the key of the song and explicit. So if the song was explicit, was it affecting the key? Was it a minor, a major, blah, blah, blah. We found that it was dependent with key. For the Billboard chart data, the artist is dependent with peak rank. So the name of the artist, it does affect how high the song is going to peak, whether it's like, oh, you have a song by Beyonce, or if you have a song by someone a little more unknown. From there, we moved into our logistic regression, and logistic regression is just finding relationships between different attributes in data. So I guess like sort of how linear the attributes are in reference to each other. We tried first with the Billboard data, but we were getting very low accuracy scores, very high standard error scores, and very low cross-validation scores. So this is probably due to the fact that the data is mostly continuous for the Billboard data. So there's a lot going on there, causing the cross-validation scores to be as low as they are. So we decided we probably shouldn't train our model off of that. We should go with the open source code's idea and train it off of the Spotify data. And sure enough, we got much higher accuracy, much lower standard error, and much higher cross-validation scores. So we decided to just go with that. That's how we were training our model. And from there, we made a decision tree, the code isn't pictured here, and created XGB regression, which was to prune the decision tree, kind of make the data a little bit more uniform for the scatter plot. And even though it is still a bit noisy, but it is able to visualize a clear band in the predicted versus predicted. So you can see that there's a pretty good prediction of what makes a song popular, which is like right in this area. From there, we decided to separate the popularity into 4 levels based on the open source code. So 0 to 25 is low, so it'll be 1. 25 to 50 is so it's 2, and so on. It goes from 1 to 4. From there, we conducted a couple of other models, but Random Forest seemed to turn out the best as it did in the open source code. So we just went with their model as well, and decided to create sample data for each of the attributes in the Spotify data based on their code. And from there, we had the data put into Random Forest for another prediction, and these are the popularity levels for just a couple of the sample songs. So 2, 2, if you were able to see it, it'd be 1. There'd be like a couple of 1s there, a couple of 3s. And then we decided to visualize the distribution. It's pretty right skewed, so most of the songs from the sample data are being read as popular, like very popular. So then we conducted a Random Forest test, this time with the filtered Spotify data, which is the intersection of the Billboard and the Spotify data where their songs overlap. And from there, we figured out the popularity level for the songs, which 2s and 1s make sense. The most popular songs would be on the Billboard chart. After that, we just predicted the peak rank based off of the popularity level. So if it was like a 1, it'd be in the top 20 to top 50, etc., until you're at the Billboard 100. And this is where the peak ranges were predicted. And then we just visualized what that looks like. So it is very asymmetric, slightly right skewed, which doesn't make sense for this model because being right skewed would mean most of the songs on the Billboard chart data are actually ranking much lower. So popular songs will be ranking lower on the Billboard chart. So, and then after we just visualized what's going on with our predictions. So we have the predicted rank in yellow, the artist mean, which is about almost normally distributed. The higher performing artists are peaking over here. The lower performing artists are peaking at the bottom of the chart, and everyone else is falling around the middle. The peak rank distribution, about the same as last time, peaking and then slowly dropping off. But you can see the predicted rank is very asymmetrical and it clearly visually does not match with the rest of the data or predictions. So just to make sure mathematically what was happening, we conducted a test for the mean squared error, the mean absolute error, the R-squared, the cross-validation scores, and they came out to be pretty low. The R-squared was negative 0.27, the cross-validation score was negative 0.43, and the mean squared error is very high at 1049. So on average, our model is overshooting by 1049, or undershooting, I guess, in this case, because it's overshooting for the rank, but that's technically undershooting where the song should be. And yes, that's how our prediction for Billboard charts rankings were done. And then here are our sources.